All right, guys. Today we are going to be talking a little bit about genetic recombination and gene linkage. Okay. So far, what we've seen in all of our examples and looking at dihybrid crosses is we've seen examples where our genes are going to assort independently of one another, meaning they are not linked. But sometimes our genes are actually located pretty close together on the chromosome, and that's when we see genetic linkage actually occurring. So, genetic linkage occurs again when our genes are super close to each other on the same chromosome. Because they're so close together, they tend not to assort independently, but kind of get inherited together as a unit when the gametes are formed through meiosis. Okay, so we kind of have to think back to meiosis to remember or understand what's going on here. All right. When our genes assort independently, and again, this is what we've seen so far, there's an equal probability of the offspring that are produced having either the parental configuration of genes, so what the parents actually have, so parental configuration, and the recombinant configuration. Okay, so parental is what the two parents have versus recombinant being a different combination of what we saw in the parents. Okay, so when our genes are located very close together, gametes actually have a much higher probability of containing the parental genotypes versus the recombinant genotypes. Okay, so the closer they are together, the higher the probability that those genes are kind of being passed as a unit into the gametes. And the reason for that is because of crossing over. Okay, so if you remember, crossing over occurs when the homologous chromosomes get really close to each other in prophase one. Synapsis occurs, right? And they pass or swap segments to the other homologous pair. So crossing over is a random process. It tends to happen at random places along our chromosome. But if there's a very short distance between the genes, there's only a very small number of places where crossing over can occur that's going to lead to the separation of those genes. Okay, so only a really small spot where crossing over can occur that leads to separation. Now, that doesn't mean that recombinants don't occur, that we don't end up with new combinations of genes. It just means that it's going to happen in pretty small proportions. So our recombinants are still going to occur. We're still going to end up with new combinations of those parental genes. It's just not going to happen as often. So to kind of understand what I'm talking about, I'm going to show you a few different examples of meiosis occurring, depending on how close or far away those genes actually are. So in this first image here, all right, we see four separate chromosomes. Okay, so we're looking at an example of genes on different chromosomes. So here, when the genes are on different chromosomes, remember those homologous pairs are going to line up randomly in meiosis, and there is an equal probability that we could end up with any combination of those genes in our gametes. So we could end up with 2 dominant, 2 recessive. We could end up with either combination of the 2 different alleles, okay? But it's all going to occur with equal probabilities. Now, if we look at our next example, we see our genes are getting a little bit closer together, but we would say that these genes are actually pretty far apart, but on the same chromosome. Here, there are so many different places where crossing over could occur. It's pretty likely that those genes are going to get swapped when the homologous pairs have crossing over occurring. And again, we're going to end up with all 4 of these different combinations of gametes made in pretty equal probabilities. Okay, because crossing over can occur anywhere on that whole chromosome, and those 2 genes are going to separate. Now, here's our exception right here. We see we've got those 2 genes on the same chromosome, and they're pretty close together. So we've got genes close together on the same chromosome. And now when crossing over occurs, it has to happen in this little tiny space on those chromosomes in order to separate those 2 genes. They're just really close together. And there's not a super high probability that crossing over is going to happen in that little spot. So what we see when we look at these percentages of our parental genotypes versus our recombinant kind of combinations of alleles is we see most of our offspring have the combinations that we see here on these homologous pairs. Okay, so we see lots with 2 dominant, all right, and we see lots with those 2 recessive. These new combinations or these recombinants we see in pretty low proportion just because those genes are so close together. Okay, so we can use this information to actually create a map of our chromosomes, so these percentages, and determine how close together our genes actually are on a given chromosome. Okay, and the way we do that is by calculating what we call recombination frequency. So recombination frequency can actually be used to construct what we call a linkage map. Okay, a linkage map is just going to be kind of a line that shows where the genes are on a particular chromosome and how far apart approximately they are. Okay, the farther apart 2 genes are, the higher the probability that crossing over will occur. And that means we're going to have a higher recombination frequency. Okay. So the higher the recombination frequency, the further apart those 2 genes are. And there actually is a maximum number to that, and that is 50%. Okay, which we'll talk about in just a second. And just so you guys know, sometimes I will abbreviate recombination frequency, RF. You see it below, but just so you guys know what that means. Okay, so recombination frequency is just the percentage of recombinants, squeeze it in there, produced in a genetic cross. So it's just a way to quantify, right, the percentage of recombinants that we have. And to calculate it, it's pretty simple. You just take the number of recombinants and you divide that by the total number of offspring. And then obviously multiply that by 100 to get your percentage or your recombination frequency. Okay, go ahead and take a second to we'll go ahead and take a second to practice that. We have an example right here. Okay, so right here we have a pretty classic example with fruit flies. Okay, and we can see in our parental genotypes, our parents here, our parents that we're crossing, we have this combination of red eyes and we have these longer wings. Okay, the other parent has, we're going to call these white eyes, and they have these shorter wings. Okay, so long wings and red eyes, short wings and white eyes are our two parental phenotypes that we are seeing here. Okay, if we are to do that cross, we end up with this number of parental and this number of recombinants. And what I'd like you to do is, using that information, go ahead and take a quick second to pause and calculate your recombination frequency. All right, so you paused, you calculated it, right? It was pretty easy. If we do this calculation, we're just taking 151 plus 154, the total number of recombinants, and dividing it by 1339 plus 1195 plus 151 plus 154, and multiplying that whole thing by 100. And what you should have gotten is approximately a recombination frequency of 10.7%. Okay. Now, one thing to keep in mind here is recombination frequency. It's not an exact measurement, but it gives us an estimate of the distance between our two genes. Okay. The highest recombination frequency that you can have is 50%, and 50% is going to correspond to our unlinked genes. Okay, so when our genes are not linked, we're going to see recombination frequencies of 50%. So they're either on different chromosomes or pretty far apart on the same chromosome. All right. So comparison of these recombination frequencies between multiple genes can actually be used to determine the order of genes on a chromosome. And this is what we're talking about when we're talking about creating those linkage maps. Okay. So we have an example right here of 3 different recombination frequencies on a chromosome, okay, for 3 different genes. We have genes A, gene B, gene C on that chromosome, okay? And when you do these, some examples are harder than others. I will say the examples we're doing right now, they're pretty simple. They get a little bit harder. It's kind of like putting together a puzzle piece. Okay, so here's my line that represents my chromosome. And what I like to do is I like to start with the largest RF or recombination frequency and put those on the outside. So here my largest recombination frequency is 18.5. Okay, so I would put gene A on one side and gene C on the other side. And I would say that those two are about, we'll say 18.5 units apart. Okay. On our linkage map, actually, before I move on, the distance between our genes is going to be expressed as what we call map units. Okay. And a 1% recombination frequency is actually equal to that 1 map unit. Okay, so I can take that 18.5 and I can say that gene A and gene C are about 18.5 map units apart. Okay, now I'm going to go to, I'll say A and B, and I'm going to say, okay, A and B, they're about 13.2 units apart. So I can put my B there. And then between B and C, those guys are about 16.4 units apart. Now, if you're looking at those numbers and you're like, that doesn't make sense. 13.2 plus 6.4, that doesn't equal 18.5, right? That actually equals 19.6. All right. So that number of map units is actually a little bit higher. That's because of double crossover events where we're having those genes cross over during meiosis more than one time. Okay, so sometimes the actual distance is a little bit off. In most of your examples, it will add up. Okay, but that actual distance of 19.6 is a little bit greater than what we see between A and C because of those double crossovers. Okay, so we have those double crossover events that can sometimes mess up our calculations. Okay, so now your turn. We've got a quick example. This one's a little bit more harder because we have a few more genes involved. So in your example here, you have genes A, B, G, and H located on the same chromosome. We see the distances of those genes below, and we want to know what is the most likely order of genes on those chromosomes. Take a second to pause and try it out. All right, so you've tried it out, right? You put together your linkage map and you followed the instructions that I gave you in this example that's just a little bit harder. So here we are going to start with the genes that have the furthest map distance from one another, which are going to be genes H and gene G. Okay, so these two genes are about 20 map units apart. Okay. The next gene that I'm going to put in there is going to be kind of the second longest distance. I'm going to go with the distance between A and H. And I see that the distance between A and H is about 18 map units. So I'm going to put A pretty close to G. And I'm going to say that between H and A, that's about 18 map units, which makes sense because I also see that between A and G, that's about 2 map units. Okay. Next, I'm going to go ahead and do between A and B. I see A and B are about 10 map units apart. So if this whole thing is 20, I'm going to put that right about in the center-ish, maybe a little bit further, like here, okay? And between A and B, right, I have my 10 map units. And then between B and H, I have 8 map units, okay? So not perfectly to scale, but the order of the genes on the chromosome then here should be H, B, A, and then G. And hopefully you guys got that right. I will see you guys in class. And if you have any questions, feel free to reach out. Have a good one.